In the previous videos, we focused on deriving the expression for the posterior distribution of the random risk variable theta I given the past reported claims, as well as on the complete predictive distribution of NI-Ti+1 given the past reported claims. These are calculations typical for Bayesian statistics, which offers, in the credibility setting studied here, a theoretically and intellectually challenging, though acceptable approach. Although theoretically satisfying, these calculations are typically difficult to perform. One suggestion to circumvent such difficult calculations is to approximate the conditional expectation of theta I given the past claim history with a linear combination of the NITs. And this is the topic of study in the so-called linear credibility approach, which enables an easy-to-compute approximation of the result. The shape of the credibility predictor for the expected number of claims in the next time period is then constrained ex ante to be linear in past observations. We introduce the intercept Ci0 and the coefficients Cit to write the predictor as a linear combination of the NITs. Note that the topics of linear credibility predictor has received a lot of attention in older work on credibility theory. We visit this approach in this video within the framework of the Poisson credibility model. The coefficients Ci0 and the Cits involved in the predictor for NI-Ti+1 are obtained from the minimization of an expected squared difference. That is, these coefficients are retrieved by minimizing the following squared error loss expression. Alternatively, one can show that these coefficients solve two other squared error loss expressions. The one in Q2, where the conditional expectation of NI-Ti+1 given the random risk variable theta I is used, and the one in Q3, where the expected value from the predictive distribution of NI-Ti+1 is used. Just to convince you that the claim on the previous sheet holds true, we show here that the minimization problems in Q1 and Q2 have the same solution. Here too, we manipulate the expression in Q1 by plugging in minus and plus the expected value of NI-Ti+1 given the random risk variable theta I. Expanding the squared sum leads to the expression printed at the bottom of the sheet. Using a reasoning similar to what we did on sheets 29 till 30, when discussing the minimum mean squared error estimator of y from random variables x1 until xn, we'll show here on this sheet that the middle term in our expression is 0. Since the first term in the expression does not depend on the unknown coefficients Ci0 until Citi, we see that the minimization problems specified by Q1 and Q2 will have the same solution. So, relying on the demonstrated equivalence between the three minimization problems, we will now focus on determining these coefficients used in the linear combination in the linear predictor. We're going to do that by minimizing criterion Q2. In this expression, we replace the conditional expectation of NI-Ti+1 given theta I with the product of the prior mean, lambda I-Ti+1, and the random risk variable theta I. To find the intercept Ci0, we take the derivative of Q2 with respect to Ci0 and we put this derivative equal to 0. This leads us to the following equality, from which our expression for Ci0 results. Now you will do exactly the same thing with the derivative of the expected squared loss with respect to Cis, where the s runs from 1 till Ti. Working out the derivative brings us the following set of equations. In this expression, the expected value of NIS is of course lambda IS, where the S refers to the coefficient we wish to find an expression for, and where t runs from 1 till ti. In the first equality, we use the expression for the covariance between NIS and NIT. In the second line of the derivation here, we replace the expected value of NIS, respectively NIT, by lambda IS and lambda IT. And we use here the expression for the total covariance. In the third equality, a distinction is made between the case where S equals T and the case where S is different from T. In the former setting, the covariance between NIS and NIT given theta I reduces to the variance of NIS given theta I. That is lambda IS times theta I. And when you take then the expected value, the first term in the expression reduces to lambda IS because theta I has unit mean. The second term then becomes lambda IS squared multiplied with the variance of theta I, and the last term is lambda IS squared. But when S is different from T, the first term in our expression is 0, because NIS and NIT are independent given theta I. That was one of our previous assumptions. The second term reduces to lambda IS times lambda IT times the variance of theta I. Putting all of this together, you will find the expression printed at the bottom of the sheet. Now at this point, you have an expression for the expected value of the product of NIS and NIT. And we need this expression to solve the expression for CIS. Here too, we also need an expression for the expected value of NIS and theta I, and that's what we will derive here. In the first equality, we use again the connection between the expected value of a product of two random variables and the covariance of these two random variables. Then we rewrite the covariance using the expression for total covariance. In this expression, we know that the covariance between NIS and theta I given theta I is 0. And the second term in the expression becomes the covariance of lambda IS times theta I and theta I. That is lambda IS times the variance of theta I. Putting all these together, we find the following result for CI0 and CIS, where the S runs from 1 till TI. As a very last step, we express the best linear predictor of NITI plus 1 as a linear combination CI0 plus the sum over all S of CIS times lambda IS. And we hereby replace the unknown coefficients with the expressions derived on the previous sheet. Rearranging the expression then brings us to the following predictor. This is the best linear predictor for each of the following three random variables. It is the best linear predictor for the true unknown mean, lambda ITI plus 1 times theta I. It is the best linear predictor for the Bayesian credibility premium, and for the number of claims, NITI plus 1 for year TI plus 1. Best here refers to the fact that the predictor minimizes a mean squared error loss. It now becomes clear that in the linear credibility setting with a Poisson assumption for the reported number of claims, the linear predictor for the a posteriori claim frequency in year TI plus 1 is a product of the a priori expected claim frequency, lambda ITI plus 1, and an approximation of the theoretical correction, which is the expected value, the posterior expectation of the random risk variable theta I given the past claim history of policyholder I. Using this expression, derived on the previous sheet, we see that a malus or penalty results when the policyholder reported more claims than expected a priori. That is, when the ni bullet is larger than lambda I bullet. We also observe that in the Poisson gamma model, the Bayesian credibility premium equals the linear credibility premium. And that kind of setting is referred to in the literature as exact credibility. It is a setting where the linear credibility premium equals the Bayesian one. Now, earlier on, when discussing the various scenarios for the reported claim history of a good, average, and bad driver, we already mentioned the severity of the discounts and penalties imposed by the credibility model. With the quadratic loss function used in our calculations, the penalties are so severe that it is impossible to implement them in practice. That's commercially just impossible. Now, alternatively, one can repeat the calculations made so far with an exponential loss function instead of a quadratic loss. This will result in reduced penalties and discounts and allows us to soften the a posteriori corrections in case of claims while keeping the financial balance. So that's an alternative loss function that one can study if you want to go further in this theory. Now let us end the chapter on credibility theory with a brief historical overview and some references to the credibility models which were traditionally studied by actuaries. So as discussed at the beginning of this series of videos on credibility theory, Mowbray, early 20th century, described the foundations of the so-called limited fluctuations credibility. Buhlmann, Straub, Hagemeister, and Jewell launched their work on greatest accuracy credibility in the 60s and 70s. And their focus was on deriving linear credibility premiums in various settings. Parameters in these models were then estimated via moment estimators. Then in the 90s, Professor Jed Vries and co-authors formalized the link between the actuarial credibility theory and the framework of linear mixed models that is widely studied in various domains of statistics. Antonio and Berland in early 21st century then continued this line of research and described the connections between the credibility theory and the framework of generalized linear mixed models. The latter two contributions are particularly interesting to translate well-known concepts from mixed models, like estimation and inference, to the framework of credibility theory, which is typically studied by actuaries. Now, the credibility model of Buhlmann is a classic model in actuarial mathematics, whereas the Poisson gamma setting mentioned explicit assumptions regarding the distribution of the response and the random risk variable, the Buhlmann model is distribution-free and only requires specification of the first and second moment of the random variables. In Buhlmann's model, we consider a random variable xjt for contract j in time period t. We consider the balanced setting where all contracts are observed during exactly t time periods. And we express this random variable xjt as m plus xi j plus xi jt. The latter are independent random variables with mean 0 and a given variance. Now, some interpretation can be added to these different components in the famous Buhlmann model. So we see that m is the overall mean, xij is the random deviation from this mean that is specific for contract j. Xij thus describes the risk quality of this contract. It also describes the heterogeneity between different contracts in the same portfolio or dataset. Xijt is a noise term. It is the deviation for year t from the contract specific mean. So therefore the xjt's are dependent when you observe them on the same contract j. And this dependence stems from the fact that these random variables share a common risk random variable xi j. Buhlmann then derives a predictor for the response xj t plus 1 in the next time period. He derives this predictor as a linear combination of the variables observed over the different time periods and over the different contracts. And he requires the predictor to have the same mean as the random variable xj t plus 1. Moreover, the predictor will be obtained by minimizing a mean squared error loss criterion. We can show with a similar reasoning as the one applied in the Poisson gamma setting that this predictor will have the credibility form. That is, it will be a weighted average of the mean of the specific contract J that we study and the overall mean x bar observed over the whole dataset, the whole portfolio, where the weight Z is determining how credible the experience on contract J is, and the Z can be expressed here using the parameters A as squared and the number of time periods T during which our contracts are followed in this balanced Buhlmann model. So this gives you a brief idea of what this classic actuarial model is about.